Okay, so what is a gas? It's a state of matter. We're more familiar with solids and liquids, but gases have a variable shape and variable volume. Right? We can compress them, we can expand them, we can move them around easily, and they sort of expand to fill the volume of the room. Right? The oxygen I'm breathing right now, may have been released from somewhere else, but has expanded to fill the volume of this room. Right? Which is a good thing and allows us to breathe. That diffusion process. Okay, so they definitely have a variable shape and volume. They expand uniformly, right? If I introduce a little bit of oxygen in this room, it's going to expand to fill the whole room, right? Same with carbon monoxide, okay, which is why gases can be so dangerous, because you can't see them and you can introduce them one place and they can expand uniformly to fill the entire room. Right, the opposite of that is also true. You can compress these things uniformly, right? So you can think about in a car, for example, or any engine, you have these pistons and you have gas inside, and you're going to move this piston down, right, compressing these little gas molecules inside. Okay, and here the gas, at least in an engine, most of the time is going to be, octane mixed with oxygen, and that compression actually heats up the gas and causes that combustion to happen. But the gas is compressed uniformly. Okay, it's not like it all just hangs out in the corner down here. It sort of uniformly compresses as we move that piston down. They generally have low density. That's the characteristic of a gas. Right, these molecules usually are far apart from one another. Right, they're not stacked right on top of each other like in a crystal lattice of a solid, or even in a liquid phase where these intermolecular forces are holding those molecules really close to one another. Okay, they're really spread out, more like this picture here in the piston, not like a solid where this crystal lattice holds these things, like bumping right up against one another. Okay, so they have a low density, they're spaced apart in an entire volume of this room. But there's still a lot of molecules, right? You close your fist, there's 10 to the 20 molecules inside there. Okay, so low density by comparison to solids or liquids. Right, and they'll also mix uniformly with other gases in a container. Okay, this piston I've drawn here is a mixture of oxygen and octane that will combust and propel your automobile forward. Okay, but those mix uniformly. It's not like all the octane hangs out on one side and all the oxygen hangs out on the other. That would be a pretty inefficient combustion reaction. Okay, so those are sort of the baseline properties of a gas, what characterizes the gas phase. Okay, and gas is usually characterized with a pressure. Right? We don't always talk about the pressure of a solid, although you could characterize that. Most often we talk about gas pressure. Okay, and in physics, 101 teaches us pressure is always force over area, right? So P equals F over A. And this is the real picture I want you to be able to develop in your mind when you're thinking about gases, right? Because they're so abstract, they're all around us, but we don't really see them. But we need to be able to picture what they're doing around us at all times, right? And even sitting in this room chaotically all around me, gas molecules are careening about, ricocheting off walls, colliding with one another, and it's a pretty chaotic environment, right? But the pressure that we characterize gases by is a function of them, hitting the surface of some container, okay, or hitting you. You're experiencing some gas pressure, right, as you sit wherever you're sitting, right? The molecules are hitting you and exerting some force, okay, and that force over the surface area that they're hitting is what we call pressure, right? So there's always these little micro events of this molecule hitting this surface right here. Okay, and there's some force because that molecule is, zipping across the room and hitting this wall, right? And it's exerting some force over that small little patch of wall that has some area, right? Call it a nanometer by a nanometer, so 1 square nanometer. But it has some energy it's hitting that area with, and it has a force that it's hitting that area with, and that's really what leads to this notion of pressure. Okay, and so the pressure really depends on how fast are those molecules moving. That's what we call temperature, some average energy of those molecules, right? And how hard, and how often. So how hard, that's their energy. How often sort of has to do with the size of the container. If it's really small and these things are zipping around, they're colliding quite frequently. A larger container, perhaps not as frequently. Okay, so we can obviously change the pressure by changing this how often, how hard nature. Okay, if the temperature increases, now the molecules are moving faster, striking these walls with more force and more frequently. Okay, so clearly pressure and temperature are going to be related. Volume is also going to be related, right? If we shrink this room down, those molecules inside are hitting and careening off the walls much more frequently. Okay, so they're going to be hitting the wall much more often, right? Which is going to lead to a change in our pressure. Okay, so we've sort of hinted on this on the previous slides. Some variables that affect gas pressure, volume, right? This is just spelling it out for us that pressure and volume are inversely related. Okay, and now that we have this picture of what really the gas molecules are doing in this room, we can imagine shrinking this room or increasing the frequency of those collisions. Okay, so the total force, over area is changing. That surface area that they're hitting is much smaller, so therefore the pressure goes up, right? If A goes down in this force over area, and pressure goes up. Okay, so as volume goes down, that surface area goes down and pressure goes up, so we call these things inversely related, right? So the opposite is true. As volume increases, the pressure decreases. Right, another variable is temperature. Right, if we force these molecules to careen about much more, with much more energy, right, that kinetic energy that should be a small v, I suppose, for velocity. And this average kinetic energy is related to temperature. Okay, so by decreasing the temperature, not changing the mass of the gas, you're changing the velocity that they're moving about the room. So as we lower the temperature, we lower the velocity of these gas molecules. So they're going to hit less frequently, and when they do hit the wall, it's going to be less forceful. Okay, so that force goes down as temperature goes down, and so pressure goes down as that force goes down. And the opposite's obviously true. As the temperature increases, we're going to move to faster molecules, more frequent collisions, and so that temperature increase will lead to a rise in pressure. Right, so we call pressure and temperature a direct relationship. Okay, and feel free to ask any questions in the chat on these concepts. If you want to do practice problems on them, I'm happy to do that. If you want to discuss other implications, that's fine. Right now I'm just sort of presenting some of the lecture topics that we'll discuss in class on these guys. The last variable we're going to talk about that affects gas pressure is the number of molecules. Okay, so clearly if pressure is force over area, okay, if I add a lot more gas molecules, then the collisions will be more frequent with the walls, and so there will be an overall increase in the force, an overall increase in the pressure. Okay, so we've had temperature, we've had volume, now we have moles of gas, or number of molecules of gas. Right? If we lower the amount of gas in some volume, there's going to be less frequent collisions, right? Again, this is the dynamic picture we want to be thinking about of a gas, these molecules, careening about off all the walls. If we lower that number of molecules, those collision events goes down, the force goes down, so the pressure goes down. Right, so all these variables, it's pretty straightforward to work out these relationships once we have this dynamic picture of what a gas really looks like at the molecular level. Okay, so we say pressure and number of molecules are directly related. And it's all well and good to have these sort of qualitative ideas, right? That variables that affect gas pressure are temperature, volume, and number of moles N. Right, that's what we've discussed thus far. But as scientists, just this qualitative idea of one goes up, the other goes up is not good enough, right? We need data, we need numbers, we need equations. And that was first sort of characterized or quantified, I should say, by Robert Boyle. Right, lived in the 17th century, and he's the guy that actually first proposed the scientific method. So he's sort of a science godfather, Bobby B, who proposed this scientific method. Okay, but he also proposed Boyle's law, which quantifies this relationship between pressure and volume. Okay, so you could do some experiments to figure out, as one changes, what is the other doing? You can go more than qualitative. So the number of moles is inherent in force equals mass times acceleration. Yeah, if you're talking about a total mass. Then that mass is going to be the molar mass, grams per mole, times the number of moles. Yeah, I tend to think in moles because I'm a chemist, but if mass is your thing, that's fine too. But yeah, the forces, if you want to relate it back to general Newton's laws and F equals ma, that's a good way to think about it. How you doing today? Be careful. I hope you're doing well. Thanks for stopping by. We're just sort of talking about characteristics and quantitative relationships of a gas. And Bobby B was the first to really propose the scientific method and the value of data, so he really ushered in all these equations that we're going to learn about. Hey, Ashley. Thanks for stopping by. Just going over some stuff we talked about in class again, and then we'll do some practice problems on it. But feel free to interject at any time, right? This can be a conversation. Malamuha. How's it going? Hope you guys had a good Veterans Day break. Ready to get back after it in class. And those not in my class, I'm sure you had a wonderful Veterans Day break, because you weren't doing my homework that evil Dr. Melko has assigned over holidays. But it's like anything else. It's like a language. If you don't use it, you lose it, right? So this was Boyle's, one of his great contributions, P1V1 equals P2V2, right? This is an indirect relationship, high pressure, low volume, or vice versa. Right, so we can calculate any one of these given the other three in this equation. And we've certainly done some of those practice problems in class. Okay, but that's just pressure and volume. We can also talk about relating these to another variable, temperature, and that's what Chuck here did, Jacques Charles. Much later, you'll see, than Robert Boyle. Boyle's law sort of helped propel forth the scientific method, and several other people over the years then developed these other quantitative relationships based on data and based on the scientific method. And so you'll see it really took a while for that to spread, right? Knowledge transfer was slow back then, but eventually enough people sort of believed in this scientific method approach. And Jacques came along here and proposed a similar type of law for gases, but relating volume and temperature. Okay, and so this is a direct relationship. As volume goes up, temperature goes up. Why? Because this quantity, or this ratio of volume to temperature, must be equal as long as N and P are constant. Right, we talked about how N, T, and V can all affect pressure. Okay, so now we're quantifying how one of these affects pressure. Right, here's P and V. So this must mean that T and N are constant, otherwise those could affect things. Here, Chuck is talking about volume and temperature. So N in pressure, moles and pressure must be constant. And then we have, even a little bit later, you'll see Lussac. Joseph Louis Guy Lussac you have to say that with a French accent, there's no other way, it's impossible not to. Joseph Louis Guy Lussac came along, and it's probably a terrible French accent, but he came along and sort of closed the gap here, finally relating pressure and temperature. So here N and V must be constant. Okay, and be careful, of course, temperature is going to be in Kelvin in all these formulas, right? As chemists, we're always going to work in Kelvin. Okay, there are instances where Celsius is fine and the conversion's not going to matter, but especially when you're working with gases in these equations, if you see Celsius or Fahrenheit, just convert it to Kelvin, right? You're probably going to have to get that over with, right? Remembering that Celsius to Kelvin means you add 273.15. Okay, so these things, should be in Kelvin, and now we can relate these different variables to one another. I'm fond of all the entertaining electronic in the background. Thank you. Okay, good. The music is approved. Is that what you mean? The background music? I don't know if that's coming through or not, but music requests are always welcome. There's no automated way. I haven't worked that into the bots yet, but if you have types of music requests, I might be able to put it on. Okay, so here's our summaries, our gas law summaries, Boyle, Chuck, and Lussac. And so we could do some practice problems with these. First, though, I just want to go over the Beyonce pyramid that we talked about in class. Okay, so you'll remember the Beyonce pyramid. Beyonce, of course, is at the top of the pyramid, Queen Bee. And then my mnemonic is Beyonce visited class today. Learned plenty. So BVCTLP. Okay, and I'm going to look at these variables I'm circling. Pressure, volume, and temperature. And the corners here, the vertices, are going to be the law. So B for Boyle's is pressure times volume, right? It's straight across here, it's multiplied. The Boyle, this is a good way to remember whose law is what. Boyle's is pressure times volume. Okay, Lussac, down here, what's next to him? Pressure, and it's above temperature. So Lussac here is pressure over temperature. Okay, and Charles down here in the lower right corner, right? Next to him is volume, and that's over temperature. So Charles is volume over temperature. Okay, so Beyonce visited class today, learned plenty. That's how I remember all these laws. Yeah, thanks. I invented this pyramid, so I don't think it's out there. I don't know. It could be. Could be that somebody else has thought about this, but I don't know. For me, it just made sense. And putting Beyonce at the top, obviously, was a no-brainer. All right, so let's think about some things we could be asked to do on an exam, or just how we might be expected to quantify these things in daily life. Okay, so here's an example question or a thought exercise. Let's sketch a graph of pressure versus volume, assuming temperature, and I guess it should say moles of gas as well, and is constant. All right, so maybe take a minute, draw the graph, or think about how you would sketch this graph to communicate to somebody the relationship of pressure versus volume, right? And this notation always is sort of y versus x to identify what you should put on each axis here. All right, so hopefully we've had a little bit of time to think about what this might look like. And you can just think about if you don't have memorized what the graph actually looks like, that's fine. You know, go back to this sort of picture of what a gas is. Right, these molecules careening about, right? Maybe it hits this wall, goes down here, hits here, goes down here, hits here. And that pressure is force over area. Okay, and every collision with the wall is some impact, and there's a force there. Okay, so what happens if we make this box much bigger? Not much bigger, but you get the idea. The impacts, right, are much less frequent. Okay, the surface area available is much larger. Okay, so as you know, the frequency of collisions is going down, that's a less total force. As the area is going up, all that's going to lead to this volume going up, pressure going down. Okay, and that conceptual picture tells you on a graph of pressure versus volume that at large pressures way out here to the right, now I should be down here, large volumes, low pressures. And, you know, conversely, at really low volumes, there's a lot of collisions with the walls frequently. So that should be high pressure, low volume. Okay, and it's actually not just a straight line, this is an inverse relationship, so it looks kind of like this swoop down into the right. You gotta say swoop when you draw it, otherwise you lose half credit. Swoop, so just like that. If I asked you a different one like pressure versus temperature, as temperature goes up, pressure goes up, so that one would be more linear, increasing up and to the right. Right, and these were, you know, displayed here back on Boyle's law. There's your high pressure, low volume, and vice versa. Okay, so that's sort of a qualitative drawing of what's going on in a graph, but let's actually calculate this out. I'll give you a few minutes to think about whose equation am I going to use here, and then go through the actual calculation and try to predict for this problem, okay, if the volume and number of moles of gas remains constant, what is the final pressure? Okay, so volume's not changing, N's not changing. I'm asked for a pressure change as the temperature changes. So identify whose law we're using there, what are the pertinent equations, and then set them up and we'll solve them. And I'll give you a minute to do that, and then we'll vote on the answer. All right, so vote in the chat for what you think the correct answer is. And Karen's already hazard a guess on the law. I can draw up here in the corner Beyonce's pyramid. Give her a little bit more space. She is Beyonce after all. You got to vote for one of the options. You can't just type it in the chat. So yours would be 2. So type 2 in the chat, just so it gets logged. The poll is showing up, right? All right, so oh, it's okay. You're here. You're trying to fix it, Ashley. You don't remember Beyonce's pyramid? Maybe you missed that day of class, but this is sort of our mnemonic for remembering what law to use. All right, so here, let's go through this one. Don't forget, type your vote 1, 2, 3, or 4 in the chat. Oh, weird. So the gotcha. I think it's not like #2. I gotta fix this polling, but it's just like the number 2. Then it should show up as a logged answer. Maybe. Unless Streamlabs isn't recognizing it. Let me see. Yeah, there we go. So hopefully it's showing up now and logging the various guesses. Don't forget, 10 bonus points are on the line here. And bonus points do not count towards your final grade. Okay, so look, in any of these quantitative problems, try to take the words out of it as much as you can, okay? And that's what I'm trying to do here just by writing down, you know, concise formulas. Hey, what's up, Jack? Welcome. We're trying to calculate pressure changes for a gas as a function of volume and temperature changes. So some Boyle's law, Charles' law, Lusak's law put into action here. All right, so now I'm trying to boil this, you know, wordy problem down to just the basics. So write on your paper, you know, volume 1 liter. That's my initial condition at 1 atmosphere. So that's my initial pressure, P1. Is heated from 20 degrees. So T1 is 20 degrees. It goes up to 110 degrees. So T2 is 110 degrees. Cool. It is cool. But sometimes it's hot, and sometimes it's cool to hot, and we have to predict based on that temperature change how this pressure is changing. So that's T2 here, 110 degrees. If the volume remains constant, so volume is not changing, V2 is 1 liter. Nice. What is the final pressure? Okay, so here I can see my volume's not changing. Okay, so if volume is not something I care about here, and I'm going to circle the V for volume in Beyonce's pyramid up here in the right, then it's not going to be Boyle's or Charles' law, because both of those involve V. I got to use Lusak's law, which tells me P1 over T1, right? Because here's P, it's above or over T. P1, T1 equals P2, T2. Right? So let's put in P1 here is 1.0 atmospheres. P2 is ultimately what I'm after, so I'll leave that as P2. T1 is 20 degrees Celsius. Yeah, no problem. We'll get to N and R. T1 is 20 degrees Celsius. But wait! I remember the good gas chemists always operate in Kelvin. Right? Kelvin is law. Celsius is acceptable. Fahrenheit is disgusting. Okay, so this 20 degrees C here is not going to cut it. That needs to be in Kelvin, right? So this, remember, as I've said, as soon as you see a temperature in Celsius, just convert it to Kelvin, add 273.15. And I'm going to have to do that for both of these. 383.15. So T1 really is 293.15. And T2 is going to be 383.15. Okay, and now I have everything sufficient. 1 divided by 293.15 times 383.15. You can always change your answer, hint hint, in the chat to vote for a different number. USA should 100% convert to Celsius. 100%. So much better. The whole, don't get me, I have a whole diatribe on Daniel Fahrenheit, but that's for a separate stream on a day when I'm much, much angrier. Today is a good day. Suffice it to say that Fahrenheit's a flawed system by a flawed man. Okay, so I get 1.3 atmospheres here. I'm gonna hurriedly change my answer if it'll let me. I don't know if it'll let you change your answer by voting or not, but one's in the chat, please. Are there restrictions to Charles and Lusak's laws? So those are really only applicable while the other variables are staying constant. Okay, so as I said back here, N and V must be constant for Lusak, N and P must be constant for Charles. And likewise, temperature and moles must be constant for Boyles. And really, these are only going to be strictly adhered to for ideal gases or gases that we can treat as ideal. And we'll learn about what that is shortly. Yeah, I guess, I don't know if it will let you, it's not updating the poll, so maybe it will only accept your one and incorrect vote here. So 100% of us voted 5.5 atmospheres, which means 100% of us got that wrong. It feels bad, man. That's a yikes. It's a big yikes for me. Damn. But that's okay. Better to make the mistakes now rather than exam day or, you know, some application when you're actually gonna have to use it. Yeah, perfect emote, Ashley. Again, we're here to learn. We're here to get better. We're not getting better, we're getting worse. So you guys are getting better. You guys want to do another one like that, I suppose? Hopefully, you know, we might be able to get something above 0% correct. Yeah. Always convert to Kelvin. Lesson learned. Alright, so let's see if do a different one here. Alright, so we'll get rid of this. We're not doing this anymore, but Let's make something else up. Lesson learned. All right. I cool the gas from 523 to negative, oh, that's going to be confusing, to negative 40 degrees Celsius. Ow. So if pressure is constant, pressure and number of moles is constant, what is the final volume? No, initial volume is 3.2 liters. Yeah, sorry, 523 degrees Celsius to negative 40. What for sig figs will make it negative 40.0 degrees Celsius. Well, that looks terrible. That looks less terrible. All right, so let's try this. We're not going to be able to move on until we get some of these right here. So let me finish the poll question here. Awkward. All right, polls up. Hopefully you're able to solve this and select your answer in the chat. Should probably move this one. There we go. How's it coming? You guys get any answers yet? We got Beyonce's pyramid here. Write down and catalog some of these values. Got a vote for 4. A vote for 3. I'm gonna vote randomly here. Just want to test the poll bot here. Two votes for 3. It's a landslide. And so it's clearly Charles's law here, V over T. So it should be V1 over T1 equals V2 over T2. Great movie, T2. Everybody's smashing 3 in the chat. Ruh-roh. All right, well, let's see. Doesn't mean they're right. So volume 1 we've identified as 3.20 liters. T1 is 523 Celsius, but because I'm a good scientist, I'm going to immediately convert that to Kelvin. So 523 plus 273.15 is 796.15. So that's my T1. Volume 2 is what I'm asked for, final volume. T2 is negative 40, so I do negative 40 plus 273.15, and this is probably where I might make a mistake. So negative 40, maybe you didn't pick up on the negative sign, but negative 40 plus 273.15 equals 233.15, and now I solve for V2. 3.2 over 796.15 times 233.15. Let me remember what the answer is. I get 0.937. Units, liters. Sweet. Hey, this is how we get better. Practice, practice. All right, so that's enough for this subject. I think we'll move on, but you know, you want to make sure you don't stop with just getting one of these right. If you got that one right, you want to go to the end of chapter and do a bunch of problems, or just Google gas law problems, Boyle's law problems, whatever it is. Oh, of course, you're very very welcome. It's a good way to do practice problems live and still maintain some interaction. I really like the Twitch live stream for being able to do that. Don't stop getting them all wrong either. Yeah. You will. You just have to do enough of them until you make every possible error. And I mean, that is a good snapshot of science in general. Like, when I go in the research lab, you know, 90% of the time stuff is breaking or not working, and it's troubleshooting and fixing those errors and doing 100 different things wrong so that when you do it right, you know, that's when you get, you know, the discovery. That's when you contribute to science. That's when you know, master something and move on to the next thing. So, I mean, I fixed something in lab 5 years ago that took me 6 months to fix, but I fixed it and now it's worked for the next 4 years. Okay, you're on to the next thing. And that's all you're doing is figuring out all these ways to do it wrong so that you can master doing it right and then use that as a building block for further advancing your knowledge. Really quick, so the outer corners of the triangle are the laws and the sides are what the problem had. Yeah, so the I could find a better way to explain that, but yeah, the corners here are the person's laws. So B is Boyle, C is Charles, L is Lusac. And then these, so purple are the laws here, orange are the variables. P is pressure, V is volume, T is temperature. Okay, so orange are the variables. And purple, there are the Guy's laws. And you don't really need to know the names of the Guy's laws in this problem. You just need to know it's volume over temperature, right? But you might be asked on an exam whose law is pressure times volume, and then you need to know that's Boyle. Okay, but solving this quantitative problem, you didn't need to know it was Charles. You just needed to know it's V over T. Okay, but the triangle also tells you that. Yeah, the list of subjects at the top is sort of how we're going through this. Still learning what a gas is. We're going on next to PV equals nRT, and then we'll talk about global warming. Okay, so we sort of have finished talking about what a gas is, but now we need one little subtle change to talk about a certain type of gas. Usually, all these laws and quantitative things we're thinking about or calculating only really apply to an ideal gas, right? My favorite type of gas because it makes things much simpler. Oh, nice. Geologist, yeah, well, you probably watch Rocket Sage. And actually, I'm pretty sure I've interacted or met you in one of the chats before. I've loved watching her and reading more about geology because it really exercises my inorganic chemistry brain muscles and trying to think about what different metals are in different gems or minerals and how that corresponds to the color we see them as. It's really cool. Press button was wrong on 2. All right, great. You've made those 2 mistakes. So ideal gas. This is sort of the type of gas I've been talking about and describing. Let me change back to red here. In this picture of what gas molecules do, right? They're careening around in perfectly straight lines, right? So rapid straight lines, and they travel in random directions. Okay, so that's one quality of a ideal gas. Okay, we also sort of assume these molecules have really tiny volumes, so that when we're talking about volume V, it's the volume of the container and the volume of the gases themselves don't take away from that volume available to them. Okay, so we sort of assume the gases are so tiny that they're not affecting the volume of the room, and the volume they're free to explore. Okay, so we assume that they have tiny volumes so that we can use V to just be the volume of the room. They're not attracted to each other. Okay, so when this one gas molecule collides with another gas molecule, right, they're not attracted and they don't stick, right? When they collide, then they go off in their directions, exactly as you would predict. Okay, so they're not attracted to each other. They collide without losing energy, okay? And the temperature tells us something about how fast they're moving or the kinetic energy. Okay, with all those things, we can use the laws we've talked about, Boyle's and Charles and Lusac. Okay, and we can also derive something called the ideal gas law. And the ideal gas law is really powerful because before, the other 3 laws, we were really talking about a change, right? You were changing the pressure and predicting the volume. Okay, or changing the volume and predicting the temperature. Okay, but here now we're thinking about just statically, for maybe a container of gas. Okay, if I know the volume of the container, maybe the volume of this room, if I know the temperature of this room, those are 2 things I can easily measure. If I know the pressure of this room, and that's something I can easily measure with a barometer, then I can work out N. Right, from this law. If I have P, V, and T, and R is a constant that I always have, then I can calculate N. So I can calculate exactly how many moles are in this room right now by taking these simple measurements. Okay, and that's the power. We're not changing something, right? This is just statically a given pressure, volume, and temperature. I can calculate the moles. Or if I knew the moles, temperature, and pressure, I could calculate the volume. Okay, so this ideal gas law allows us to equate all these variables to one another. Okay, importantly here, R is the gas constant. It has really funky units. Right, the unit of volume is just liters. The unit of pressure is just atmospheres. But R is sort of responsible for being able to equate liters, atmospheres, which are the units of pressure times volume, equating that to a unit like Kelvin. So all these units, liters times atmosphere per mole Kelvin, right, that belongs always with and next to 0.0821. Okay, but if we're going to use this gas constant, we really have to be careful now with the units of pressure. If we're using this gas constant, then pressure must be in atmosphere. If we're using this gas constant, volume must be in liters. And temperature, no surprise, is going to be Kelvin. Right? Back here for our previous calculations, okay, you were asked for liters, but this could have worked with torr or bar or Pascal or milliliters mercury, whatever pressure you wanted to work. Or volume could have been milliliters, right? Or centiliters or whatever, right? Cubic meters, doesn't matter. Beginning volume would be same units as end volume. Here, though, the units for pressure and volume have to be atmospheres and liters correspondingly.